Now let's look at the second question, which shows a horse that is leaning on the wall. And the problem asks us to calculate the force the wall exerts against the horse. So here is the diagram of the horse leaning on the wall. We are given two forces. The force, the normal or support force exerted by the wall on the horse, which is directed to the right, and the weight force on the horse that's acting at the center of mass or center of gravity of the horse, which is indicated at this point here. Now let's draw our free body diagram, because although only two forces are shown in the problem, there are actually other forces that are not shown. So let's draw the free body diagram. Okay. Because as I've mentioned earlier, whenever we're doing torque problems, the point where the force acts is also important. So when we draw our free body diagram, we would like to specify where the forces are located at. Okay, so the horse is leaning on a wall. So when I draw my free body diagram, I would represent the horse by this diagonal line. Okay, and we are already given, it's a diagonal line because the figure shows the horse leaning on the wall, and you sort of can represent its position by this diagonal line that's leaning towards the left. Now, the problem already shows us that there's a force on the horse by the wall, which is the support force provided by the wall. Right, and there's a weight force because of the horse's mass. So notice how the weight force is located higher compared to the wall. You see how the center of mass point is higher relative to the normal force provided by the wall. So when I draw my free body diagram, I put my weight force higher relative to the point of the support force acting on the horse by the wall. Now there are two other forces that are acting on the horse. Can you think of which two forces those are? So if you look at this diagram here, there are two other forces that are not shown that are acting on the horse. Notice how the ground is supporting the horse from below. So you should have a normal force that's pointing upwards. This is the support force provided by the ground on the horse. Okay. And the problem didn't say that the ground was smooth, so we can say that there should be static friction acting on the horse's hoof. Now, which direction will the static friction be? So notice that by the way the horse is leaning towards the left, if the horse were to slip, the horse will slip towards the right, and therefore there should be a static friction force that's pointing to the left. So those are the two other forces that are acting on the horse. There's a normal force provided by the ground on the hoof that's pointing upwards, and there's a static friction that prevents the horse from slipping, and the static friction force is pointing to the left because it's opposing the possible slip of the horse, which will be towards the right if the horse were to slip. So let's add those two forces onto our free body diagram. So there's a normal force that's upwards and a frictional force that's pointing to the left. So this is the normal force that's upwards and the frictional force that's pointing to the left. Okay, so this is our free body diagram. It shows us the four forces that are acting on the horse. The next step is to choose the pivot point about which we calculate the torque. Again, a good choice of pivot point would be the point where you have an unknown force, or the point where you have two or more forces that are acting. Because then if you put the pivot point at the point where there are two or more forces acting, then you are able to eliminate those two or more forces. So in this case here, we have the normal force and the frictional force acting at a common point. So it will be a smart choice to put the pivot at this point where the normal force and the frictional forces are acting. Once you have chosen your pivot point, so again, pivot point is arbitrary. It's up to you to choose where you put your pivot point. But once you've chosen where your pivot point is, you determine your lever arms or your moment arms. So the lever arm goes from the force to the pivot point, and it's perpendicular to the force. So we have here the force exerted by the wall. Okay, so you can extend that force and draw a line perpendicular to the force and passing through the pivot point that you've chosen. Okay. So this will be the lever arm between the wall and the pivot point that you've chosen. So the problem says that the force on the wall to the ground is 1.2 meters. So that's actually given in the problem. So see how this support force provided by the wall is 1.2 meters above the ground. Okay. Right. We are also shown that the center of mass is 0.35 meters away from the horse's hoof. So that gives you now the pivot point between, the lever arm between the weight force and your chosen pivot point. Right, so the weight force here is shown to be 0.35 meters away from where the hooves are. So going back to our free body diagram, okay, to find the pivot point, to find the lever arm between the weight force and the pivot point, okay, you extend your weight force and draw a line perpendicular to the weight force passing through your pivot point. That will be the lever arm for your weight force, which is equal to 0.35 meters. Okay. Right, so now that you have your lever arms and your forces and your pivot point, you now do your net torque calculation. So you take the net torque about the hoof, which is your chosen pivot point, about the hoof, which is your chosen pivot point, Right, so let's do the weight force. So yeah, so torque is equal to, let me just rewrite that. Torque is equal to lever arm times the force. So looking at the weight force, the torque due to the weight force will be the lever arm, which is 0.35 multiplied by the weight force. Okay. Now, will this torque be positive or negative? Notice that the tendency of the weight force is to pull the horse downwards, and relative to the pivot point, that will cause the horse to rotate in an anti-clockwise direction, and anti-clockwise gives us a positive torque, so that will be a positive 3.5 multiplied with the weight force. Now for the frictional force and the normal force, the torque will be equal to 0 because the lever arms are 0, and that's because we put the pivot point where the friction and the normal forces are. So we don't have to bother ourselves with the frictional force and the normal force. We now look at the force from the wall. Okay, right, so the torque, because of the force on the wall, force from the wall, will be equal to the lever arm, which is 1.2 meters multiplied by the force provided by the wall, F wall. Okay, now determine whether that's a positive or a negative torque. Notice how the wall has, the force from the wall has the tendency to pull the horse to the right, okay, and relative to the pivot point, that will cause the horse to rotate in a clockwise direction. So clockwise will have a negative torque, so that will be a negative 1.2 multiplied with the F wall. So I'll just remove the unit meters just to minimize the clutter. Okay. So the torque due to the force from the wall is negative 1.2 times F wall. Okay, so we have now accounted for all the forces. We only have two forces that will contribute to the net torque. Again, because the frictional force and the normal force will have 0 torques, because we've put our pivot point where the frictional force and the normal forces are. Okay, so the net torque will just be due to the weight force and the F wall, and the sum of those torques is equal to 0. Right, we are being asked to find for the F wall, the force exerted by the wall. So we go ahead and rearrange this equation to isolate F wall. So if I added 1.2 times F wall to both sides of the equation, then I have 0.35 W on one side and 1.2 F wall on the other side. I now divide both sides by 1.2. I have 0.35 W on one side divided by 1.2, and that's equal to F wall. Okay. I just flip this so that F wall is on the left hand side. Right. Okay, W, the weight force, we can calculate because we're given that the mass of the horse is 4 kilograms. So given the mass of the horse is equal to 400 kilograms rather. Okay, so we can now solve for F wall. 0.35, weight force is mass, 400 times gravitational acceleration, 9.8 divided by 1.2. That will give us an F wall value of 1143 newtons. Right? So you can see in this example how a seemingly complicated free body diagram involving 4 forces can actually be reduced to a torque equation that involves only two forces. And we were able to do that by choosing the pivot point to be at the point where there were two forces, and therefore that eliminated two of the unknown forces, allowing us to calculate for the unknown force exerted by the wall on the horse.